Hey, how's it going? We're back from Cancun. I just solved a whole bunch of linear algebra determinant problems from this book. It got pretty, I don't know, it doesn't look as warped right now, but it got pretty beat up while I was in Cancun. I was literally on the beach just solving a whole bunch of determinant problems because I'm a freaking nerd, y'all. So you can see it, nerd tan. I got the nerd tan, the V-neck nerd tan while I was out there in Cancun. I had a wonderful, fantastic week. First time I've ever done anything like that, like an all-inclusive resort, just sipping Mai Tais and pina coladas and non-alcoholic virgin mojitos while working through this book, Shilov, Determinants. So, I just want to work through, get a couple repetitions in. I'll just be reworking some of the problems that I did last week. And to that point, oh no, my tiny notebook is in the other room. It'll take a moment to go grab it. It won't take very long. But, let's see. So we are, all of these dotted ones, I'll grab a couple of those and we'll work through some of those right now. On the plane, I just wrote out every Shilov problem from section 1 on determinants. Also, I should just say, hello, my name is John. This week we're going to be working through linear algebra on stream and doing some determinant problems. I hope that we will get into Markov chains this week. That's my goal. And yeah, so here are some of the problems from Shilov that I did those in the past. And now we might do Shilov 1.5, we might do 1.6. I think 1.6 was pretty cool. I enjoyed this one. These are pretty tough though. 1.7, calculate. This one was super tough for me. Like, it took me a couple of tries. So Shilov just jumps you right in. He's just like, don't complain. Just do all the determinant problems. Don't complain and just do them. And then you just do more and more determinant problems until you stop complaining. So if you're Axler, you might get a little annoyed at this book. My guess is that Sheldon Axler, who wrote Linear Algebra Done Right, my guess is that he learned linear algebra from this book and he's still mad at all of these super hard determinant problems from section 1. And that's why he wrote his book, which takes the complete opposite approach. His book doesn't do determinants until the very end. He builds all of linear algebra without determinants, whereas Shilov, problem 1, just lots of hard determinant problems. So I thought that a lot of these were pretty cool problems. We'll work through some of them. 111 was tough, but, I guess it's good for you somewhat to do all these. I'm going to be right back and get my tiny notebook so that I have answers just in case I need them. Be right back. Cool, so I'm back. Hello. This is going to be fun. We're back online. We're back on YouTube. Hey, we already got a like. Thank you, somebody, for the like. Somebody watched for 20 seconds and gave it a like. I appreciate you, whoever you are. Okay, which problem do we want to do first? I think that... Let's see. I liked 1.5. Let's just jump right into 1.5. I think 1.5 was a good one. So, for anybody who's new, my concept here is that this is a practice stream. It's not going to be the most polished ever tutorials on math. It is literally just me practicing. So, take it or leave it. I think I can get some good work done here. Whether or not it's perfect. All right, so maybe we'll be blue. Let's call this a solution. It's not quite a proof, but so we want delta. Delta is this determinant, AM plus BP, CM plus DP, AN plus BQ, and CN plus DQ. Okay, and he said use the linear property of determinants to calculate this. So I think that this is before we know, this is before we know the 2x2 formula. I think that there's a smarter way to do this one. So a property of determinants is that for any column or any row, you can add or subtract other columns and rows. So what I'm going to do is column, he does everything in columns, so I'm going to do the same. I'm going to do column 1 minus column 2. So I'm going to replace column 1 with column 2. AM plus BP minus AN plus BQ. You can see that that will be A times M minus N plus B times P minus Q. And then the second column is still going to be this. All right, and then looking at the second row, so first column minus second column is going to be C times M minus N plus D times P minus Q. Cn plus dq. Okay, and now, let's see, what do we have next? How does this one go? I haven't done this in a little bit. Use the linear property of determinant. So I think that this is before we do expansion by cofactors. So 1.44. How does this go again? Oh, yes, okay. All right, so in section 1.44, the linear property of determinants. The theorem is that, I was thinking that it was something along these lines. If all the elements of the jth column of a determinant D are linear combinations of two columns of numbers, i.e., oh yeah, okay. Okay. I think I remember this kind of. Okay. So, this thing, Shilov has this sort of thing rewritten as dj lambda bi plus mu ci equals lambda dj bi plus mu dj ci. Okay, there's a lot of subscripts and a lot of indices that Shilov uses everywhere. Okay, so in so this is where DJPI means the determinant obtained by replacing the elements of the jth column of D by the numbers PI. Okay, so you replace the determinant in the jth column with the number lambda. Yeah, with whatever's inside this parentheses. So then this is the same as m times determinant MD1 MD1A plus P D1 with the wait, no. This would be M, which is the common factor in the first term in the first column, and then replacing with the column vector AC plus P times D1 replaced with BD. So now this is going to be M times the determinant. So the first column is just AC, and now the second column is AN plus BQ, CN plus DQ, plus the determinant BD, and then the second column is still AN plus BQ, CN plus DQ. So, yeah, we have this like linear property where we can split this into two separate determinants, taking out these scalar factors and taking out this like addition into two separate determinants. I don't know how to phrase that better right now. I hope that's good enough. All right. So, oops. Let's just, okay, and now on this one we can replace this with n determinant AC plus Q determinant AC BD plus P times determinant N determinant BD AC plus Q determinant BD, 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 BD. So that's pretty small on the edge there. I hope you can see it. Hey, Tijuana, how are you? Just saying hi. Have to watch the replay later. Good to see you, man. That's cool that you want to watch these replays. This is such a nerdy stream. I just got back from Cancun. Cancun was incredible. It was so sunny. So I'm a little bit tanned, I see, which is cool, I suppose. All right. Oops. I'm going to copy all this again. Down here. And now, Shilov somewhere says that if two columns are the same, then they vanish, then the determinant vanishes. The vanishing, where is it? There's a few ways that we see that the first determinant there vanishes. Yeah, so 1.43 corollary. So, yeah, where should I write this? 1.43, a determinant with two identical columns vanishes. Okay. So vanishes is fancy talk for equals 0. So we know that this term vanishes, and then what we have is MQ times ABCD plus P, let's do NP. Oh, and this other term with BD, those two columns are identical, so this one vanishes as well. And now we have NP. Remember that a field is commutative, so you can swap the order of multiplications. BDAC. And we're going to be fancy and say ABCD minus NP ABCD. So what I did here is I interchanged two columns. And anytime that you interchange two columns, the determinant has the same value, but it's negative. How does he state that? Let's get it exactly stated the same way. Where does this happen? The antisymmetry property. The determinant changes sign when two of its columns are interchanged. Okay. The determinant changes sign when two of its columns are interchanged. And he proves that. In 1.42, the antisymmetry property. And two identical columns vanishes. That's a corollary, because if they equal each other with opposite signs and they equal each other, the only number that equals itself when it changes the sign is 0. So that's how you get the identical columns determinant equals 0 property. So this is by antisymmetry. interchanging columns changes the sign of the determinant. Okay, and now we have MQ minus NP times this determinant A, B, C, D, and that is MQ minus NP times AD minus BC. Somewhere in the text he proves, or you learn somehow, the 2 by 2 determinant calculation is done by these diagonals, A times D minus B times C. So I'm pretty confident that that's the answer in the back of the book. It might flip the order of those two multiplications, but I think that one makes sense. I have to be right back, super quick. Be right back. All right, hello, we are back. So that solves this problem 1.5. Let's take a look at another one to do. Which one do we want to do? Oh my god, okay, this one. Yeah, these numbers are divisible by 17. Show that the determinant this is also divisible by 17. Ooh, I thought that this one was cool. I was like, it took me a moment to figure it out. Let's tackle it. How does this go again? Copy. Is this one we want to solve? I think so. I think it's a good one to work. Okay. These numbers are divisible by 17. Show that this determinant is also divisible by 17. Okay, so 20604, 53227. So the rows equal these numbers. But they're the digits of those numbers. So, cool. Solution. Or proof, I suppose. We could call it a proof, because we are showing something. How do we do this? Okay. So, 20604 equals 17 times some number A, 53227 equals 17 times some other number B, 25755 equals 17 times some other number. Let's not use A, B, C, D. No, yeah, let's do it. 25755, 20927 equals 17 times some other number D. 78421 is the last one. 78421 equals 17 times some other number E. Okay, so these are, Shilov tells us that those are all divisible by 17. And a problem like this definitely is implying that you should be able to do it, you should be able to show this divisibility without actually calculating the entire determinant. Because this is a huge determinant, A 5 by 5, it's going to take you a while to calculate. So there's got to be some smarter way to do it. I'm going to call this determinant D. And then what we can see is 20604. I can see that we're doing, in some way, we're using the powers of 10, because these are the digit expansions of the determinant D, or of those numbers that we have. So 20604 is 2 times 10 to the 4th, plus 0 times 10 to the 5th, plus 6 times 10 to the 4th, plus 0 times 10 cubed, plus, oh wait, I screwed that up, oops. 0 times 10 to the 3rd, 6 times 10 squared, 0 times 10 to the 1st, and 4 times 10 to the 0th. This thing is similar. Yeah. I'm just going to say etc. here. So we're considering the base 10 expansion of these numbers. Then D equals, we can see that number 2 as 20604 minus 20604 plus 2, etc. So I'm only writing in the first coordinate so that we can see how this works. Let's make that a little bit more clear. Let's make that more explicit, that is. Then A11, the first coordinate, which is 2, is the same as 20604 minus 20604 plus 2. So I just added and subtracted a number, which is the same as adding 0. And then now we know that this is 17 times something, whatever it is. Or why don't we do it as 2 times 10 to the 4th plus 610 squared plus 4 plus 2 minus 17 times some number A. So here I subtracted out the 17A, or like I'm using the fact that that Shilov told us that it's divisible by 17. Then what we are going to use is the fact that we have this digit of the digit of the 10 to the 4th place. We have that twice. 2 times 10 to the 4th plus 1 plus 6 times 10 squared plus 4 minus 17a. And then we'll do that for all of those terms in the first column. So then by the linear property of determinants D equals 10 to the fourth plus 1 times the determinant, replacing the first column with that number, or with the digits of 10 to the fourth, which is 25227. 25227, 0604, 0604, 3227, 3227, 5755, 0927, 0927, 8421, plus, now we can replace, now this is going to be 10 to the third, and then we replace the first column with the digit in the 10 to the third place, which in the case of A11 is 0 times 10 to the third, right? Well, 03508 is going to be the first, 03508, but it's also going to be the second column, and then we have some other stuff. And then on this one, we're going to have, on the 10 squared term, 62794 something, 62794, and then some more numbers. So each of these terms is going to vanish because 10 times D, we call this column, we replace the first column with the fourth column, which maybe I'll denote as A I4 or something. The fourth column of the matrix A, which vanishes this is probably clear if I call this like the fourth column and then the fifth column. And each of these is going to vanish. Then we still have this other term of minus 17 times minus 17 times A, B, C, D, E, 0, 6, oh wait, no, 0, 6, 0, 4, 3227, 3227, 5755, 5755, 0927, 0927, 8421, 8421. So now D equals 10 to the fourth plus 1 times D. This is the exact same matrix that we started with. So D equals 10 to the 4th plus 1 times D minus 17 times some number, whatever that is. I'm going to just call that the number K. But whatever this is some integer. This is going to be some integer K. So 17 times K equals 10 to the 4th times D. So I added 17K to both sides and then subtracted D from both sides. Because 17 does not divide 10 to the 4th. 17 doesn't divide 10 to the 4th. It neither has the greatest common divisor of both. They are relatively prime. 17, since the greatest common divisor is 1, in other words, they are relatively prime, then this implies that 17 divides D. Because 17 because the greatest common divisor of 17 and 10 to the 4th equals 1, either 17 divides D or K divides D. Right? Well, since the greatest common divisor of those two numbers is 1, we know that 10 to the 4th is going to divide K. So D equals 17 times some other number, K divided by 10 to the 4th, which we know divides K. So it's like 17 times some other number, K2 or something. Therefore, D is divisible by 17. Yeah, I think that was okay. There's, this is not the most clear little presentation there, but I'm pretty sure that that's right. Let's keep going. What's next? We did Shilov 1.6. So we've done these two. They're okay. I'd say, I don't want to call them green. They're not easy, but I have done a repetition of both of them. Yeah, I'm going to go ahead and give them a green because I don't want to come back to it relatively soon. Number 7. Let's do number 7 next. Yeah, this was tough, I feel. Calculate these determinants. All right. It wasn't so tough. It's more just great practice, honestly. Really, really good. I feel I am much better at calculating determinants now after all of these really tough problems. All right, so Shilov 1.7. Let's start out with this first one. Okay. All right. So, on something like this, hey Jeffrey, good to see you, man. How are you? On something like this, I'm going to look for patterns. And looking at this again, I see this nice pattern. These have the same tens and ones places. Like, and then looking a little bit further, we can see that if we subtract one from the other, we're going to get 100. So I'm going to just recopy this first column, 1014, negative 342. Or actually, yeah, let's do that. So a property of the determinant is that you can add or subtract. You can add a multiple of a column to another column. But you have to, we can add the third, or we could subtract the third column from the second column. Which means if we subtract the third from the second, we're going to get 100s there. Yeah. So we can subtract the third from the second, and now we can factor out a common factor. So I'm going to factor out 100, 246. The second column is 111. We factored out that 100 common factor. 1014, negative 342, 327, 443, 621. Also, if it's not obvious, if anybody's seeing this after the fact, pause and try to solve this yourself before watching my solution, right? Like, I don't want to say that every time, but like, pause and try to think about it on your own. All right. Again, we can pull out common factors. So I'm going to divide the first column by 2. 123, what is this, 507? And negative 171, right? 111. We can subtract a multiple of a column from another column. So I'm going to subtract 327 copies of the second column from the third. In other words, I'm going to subtract 327 from each of these numbers. So 443 minus 327 is 100 and I'm confusing myself. 443 minus 327, 13, so 6, 3, 2, 116. All right, and 621 minus 327 is 4. Almost 9, 294. Does that look right? Yeah. Okay, so 621 minus 327 is 294. Now, what we can do is we can factor out a 3 from the first column. No, this is not Strang. Strang is the easy book. We're on the tough book today. Today we're on Shilov. And in fact, Strang Oh wait, no, I'm thinking of Axler. Axler hates determinants. Shilov loves determinants. I think Strang doesn't mind determinants nearly as much. But hey, how's it going, Amit Mital? How are you? I do have my copy of Strang now. But yeah, this one is, today we're working Shilov. Shilov is tough. If you want to try to work this yourself, here is the determinant. Calculate this determinant. Pretty large numbers. You can just, multiply all these humongous numbers and, just run them through a calculator. But I think that the purpose of this problem is to learn and practice some determinant properties. So we can factor out a common factor of a column. Let's do this in 2 steps. I was going to try to do it in 1 step. So first column is the same, negative 171. Second column is 1s. I just factored out a 2 from the third column. So this is 58, and this one is 147, right? Okay, next. So the third column is not divisible by 3 so I'm checking divisibility by 3. 5 plus 8 is 13, which is not divisible by 3. So I know that 58 is not divisible by 3. It is 29 times 2. Does 147... Does 29 go into 147? It would be like about 4 or so. 4 times 9... I don't think so. 4 times 12, 5. Yeah, no, I don't think. 147 is not divisible by 29. Okay, but the first column is divisible by 3. So this is going to be 1200 times 123 is 41 times 3. 507, what is that? 507 divided by 3. 6, 9. 169. And negative 171. We're going to get negative 5 and 7. Yeah, so negative 57. 111. What we can do is we can subtract... Well, I don't want to subtract the second column from the third because then we get rid of that delicious, beautiful 0 that we have there. So I'm going to keep this like this. But we can add 57 copies of the second column to the first, in which case... yeah, we don't have any more divisibility by 3, but we can add 57 to the 57s to the first column. So 169 plus 57 would be 226, right? Yeah, 226. 41 plus 57 is going to be 98. 111, 0, 58, and 147. I don't think there's anything more we can do to that third column. Now we can factor out a 2. 49, 113, 0, 111, 0, 58, and 147. And now I think that this is in a reasonable state to where we can just do the calculation. So to do a 3 by 3 determinant, you can copy the first two columns. And then this is called Sarus's. I learned this recently. Sarus's rule. The rule of Sarus. Where do you get a majority of your problems from? I get them from books. What about you? I'm using Shilov. I'm using Strang. And I am using Adler. But mostly Shilov. I've been working a lot of Shilov recently. So this is going to be 2400 times 49 times 147 plus 1 times 58 times 0, 0, 0. Okay, and Sarus's rule is that we add these diagonals and then we subtract these diagonals. Okay? Let's see if we got the right answer this time around. So we got a couple of zeros. 49 times 147 minus 0 times 1 times 0 minus 49 times 58. 49 times 58 minus 147 times 113. Right? Okay. Let's keep trying to be clever and see what we can do, mental math and whatnot. This is the same as 147. I'm going to factor out a 147, 49 minus 113. Minus 49 times 58. 49 minus 113 is the same as negative 113 plus 50 minus 1. Whatever. 113. Let's just do it. 13. Here's a 4. Oh wait. Yeah, 10 minus 4 is 6. And then, alright, so 64. This is 147 times negative 64 minus 49 times 58 times 2400. Let's pull out some factors of 2. 4800 times, we've got, I'm going to factor out the negative. Then we have 32 times 147 minus 29 times 49. I don't know if I got the right answer. I bet that I feel like I missed this. I feel like I made a mistake somewhere. These numbers are not feeling as familiar. 36 plus... Wait, 81, 4 times 9, 36 plus 8 is 44. Yeah, 0, 18, 9. 1, 12, 14, 14, 21. Oh wait, I factored out the negative, so this one should be a positive. And we've got 4704 plus 1421. 5704 plus 421. 6104. What is this? 6125? Is that right? Negative 4800 times 6125. I don't feel like doing this one. Let's just get it. Let's just do it. Let's ask ChatGPT. I did this all by hand on the beach in Cancun last week. I enjoyed it. I did get it correct twice in a row. I think I just got it again. This number does look familiar. 400,000. Yeah, I think that's the correct number. Look at that. We got that determinant again. We're getting so good at determinants because of Shilov. Shilov is tough. Yep, that is correct. All right, 29,400,000. Thank you, Shilov. Thank you for that really tough problem. Cool. So that was this first of the two annoying, hard determinant problems. Now, this second one gave me a lot of trouble, and it's because I did not realize that Sarris's rule only works for determinants of size 2 and 3. Determinant of size 5, because Shilov is an asshole, doesn't work that way. Okay, so I had to do this one a couple of times. This one is hard. Yeah, and yes, Shilov is tough, but it's good. It's really, really good. I've heard great things about Shilov. I haven't learned linear algebra yet, though. You will. You will. If you keep watching this channel, you should learn linear algebra from me. Because I actually, no, it would be a bad idea to learn linear algebra from me. But, you know what? It would be fun to have you, in any case. Okay. Andrew, Herder, I don't know what you're talking about. Good. You can learn. You can learn a little bit. How's it going, everybody? What's going on with y'all? What's the best way to do this one? So, you can subtract rows, you can subtract columns, all sorts of good things like that. Let's see. What's the best way to do this? I think that there's like some really clever way. I think that there's a more clever way than how I did it. But let's just do it. All right, so what I did was I kept the first row, and then I kept subtracting the first row from the first column. I subtracted the first column from the second, so we would get -1, 3 minus 1 is 2, and then we get a bunch of zeros. And then subtract the first column from the third, so 1 minus 2 is -1, 1 minus 1 is 0, 4 minus 1 is 3, and then 1 minus 1, we get a 0 and a 0. Subtract the first column from the fourth, and we get another -1. 1 minus 1 is 0, 1 minus 1 is 0. 5 minus 1 is 4, and then 1 minus 1 is 0. And now the first column from the last one, we get another -1, 0, 0, 0, 6 minus 1 is 5. Okay. Now that we have this, we have a lot of zeros, which makes it easier to calculate. With linear algebra, you can... Ooh, wait, okay. I think I see something nicer than what I did. Ooh, this is way better. Now you can add rows to other rows. So I can add, and you can also subtract rows from rows. So if I take the first row, does it work out any better this way? I'm confusing myself. I am confusing myself. All right. If I double the first row, I'm taking a different path. We're going off the path that I did, but I think that this is going to be nicer than the horrible mess that I used. So if I double the first row, then I have to balance it out by multiplying by a half for the determinant. So what I'm getting is 4, -2, -2, -2, -2. Okay? 1, 2, 0, 0, 0. 1, 0, 3, 0. I'm just copying everything. Now I'm going to add the second row to the first row. So 5, 0, add the second row. Yeah, we're always adding the second row to the first. So now we have -2, -2, -2, and then everything else is the same. Then I'm just going to say ... Everything else is like ditto, the same as the prior matrix. So just keep referring to that prior matrix. Now I can I don't know. Yeah, I can triple the first. I can triple that first row. 15, 0, -6, -6, -6. I'm going to say ... and then the third row, I'm just going to rewrite. Actually, let's double the third row. So if we double it, then we need to write our scaling factor of the matrix. 2, 0, 6, 0, 0. I don't know if that's a good idea or not. Could just do a cofactor expansion at this point, but right now I'm trying to be clever. Add that third row to the first row. 17, 0, 0, -6, -6. And then maybe at this point I divide the third row by 2 again, just to get back to where we were. And before we get too far, let's rewrite the rest of the matrix. 1, 2, 0, 0, 0, 1, 0, 0, 4, 0, 1, 0, 0, 0, 5. Okay. We could expand by cofactors on the second row or the last column. Any of these that have a bunch of zeros, it'd be useful. But it's nice to do as much as you can, I find, of simplifying the numbers as much as you can. Like, add the last row to the first row. And then add the fourth to the first. And now let's just get our, let's do a cofactor expansion just to be done with it. Expanding by cofactors on the second row. This is going to be negative 1 over 2 times 3. 1 times the determinant. So the way that a cofactor expansion works is we're going to take a element of that row, do positive minus, positive minus, positive. So we have this minus sign because it's in the second row. Determinants are this multilinear operator with this anti-symmetric property. And okay, so you get that factor, and then you slice out the column and the row that it's in, and then you write the determinant of the remaining minor matrix. 0, 3, 0, 0, 0, 0, 4, 0. There probably was a cleaner way to do all this, but that's okay. And again, you use positive, negative, positive, negative, positive. So now we're going to subtract 2 times 2 times the matrix that's obtained by slicing out the second column and the second row. So this matrix is 19, 0, negative 2, negative 1, 1, 3, 0, 0, 1, 0, 4, 0, 1, 0, 0, 5. And then the other cofactors are zeros. So that's it. Now, I'm going to just write negative 1/6. Well, this one has zeros in the entire first column, so I already know that this determinant equals 0. So that's great. then if we multiply negative 1/6 times 2, then we have 1/3 times 19's, this determinant. There has got to be a clever way to solve this. There has got to be a clever way. I really hate expanding matrices by cofactors. Like, it just feels like the wrong way to solve a determinant. So I'm going to take the second row and subtract the third row. Then we're going to get a 0, 3, -4, 0. I'm going to take the third row and subtract the fourth row. 0, 0, 4 minus 0, 0 minus 5. And then we still have this one left. Now, we can factor out a 2 from the third column. 19, 0, minus 1, minus 1. 0, 3, minus 2, 0. 0, 0, 2, -5. And 1, 0, 0, 5. And I think now we should just do the cofactor expansion, unless we wanted to try to be really, really clever. I'm going to expand this determinant by the first column. So this is 2/3 times 19, and then the determinant 3, -2, 0, 0 to -5, 0, 0, 5. Plus, minus the determinant obtained by slicing out the first column and the last row. 0, -1, -1, 3, -2, 0, 0 to -5. Let's see if we got the right answer, because I kept messing up this problem again and again. Like, there's so many little calculations and so many places where you can do something wrong in this. Okay, in this first determinant, let's take out a factor of 5. Then we have 5 times 19. And I'm just going to keep things simple. Something that's lovely is that once you do get a row of zeros with 1, 1, like 0, 0, 0, 1, then you can clear out all the others in that corresponding column, because you can then just add 5 copies of that third row to the second. And then this would be 0, 2, 0, but I'm going to go ahead and pull out that 2 as well. So 2 times 5 times 19. And then add 2 copies of the second row to the first to clear out a 0 above it, and then pull out a 3. 3 times 2 times 5 times 19, and then that determinant is just 1. Here, I'm going to rearrange I'm going to swap the first and second rows, and then I'm going to multiply the second row by -1. So the sign stays the same. 3, -2, 0, and then we have 0 to -5. So 2 divided by 3, here we have, I'm going to distribute that 2/3 through. Yeah. Then the 3's cancel in this first term, and we have 4 times 5 times 19 minus 2/3 of this determinant. 3, -2, 0, 0, 1, 1, 0, 2, -5. 20 times 19 is 380. Is that right? Should be. Oops. I need a break. So 20 times 19 is 380. Yeah, I was correct. 380. I'm going to add the third row to the first. 3, 0, -5. Or, yeah, I don't know. Whatever. Instead of trying to do, what's it called? Row reductions and adding columns and adding columns or adding rows to one another. I'm just going to expand by the cofactor of the first column. I'm going to expand by the first column times 3 determinant 1, 1, 2, minus 5, 380 minus 2 times -5 minus 2. Yeah. 380 plus 14. And I'm pretty sure that that's correct. I think that that's right. I did a pretty different solution than I did in Cancun. I don't know if that's because I've got another practice repetition in and I'm getting better at these determinants, or if it means that I'm stressed out because I'm on YouTube and going a different direction. Or it's just that it's so easy to take many different paths when you solve a determinant. And that is correct. 394 was correct. Look at this. We're doing it live and we're getting answers correct. How great. Hit the like button. Leave a comment below if you enjoy this. It means a lot to me. Yay, we got it. How's it going, Nate Programming? How are you? We got 3 for 3 so far. No mistakes. So Shilov 1.5 was fun. Use the linear property of determinants to calculate this thing. Then we did this one. Oh no, we've done 4 in a row. All correct so far. Show that this determinant is divisible by 17. That worked out decently well. And then we calculated both of these determinants. So Shilov is the opposite of Axler. Axler is like traumatized by how annoying determinant problems are. And Shilov is just like, stop complaining and just do it. Are you doing this for fun or test? Both? like really for fun. I'm doing this for fun. I'm trying to rebuild my mathematics skills. I used to study math. I did a bachelor's in pure math like 15 years ago. And then ever since, I haven't really been doing math very often. Now I'm trying to build up math as a hobby, as something I'm doing for fun. And I think that YouTube is a good way to share my passion and love of mathematics. So here I am sharing math with the world, with you all. How's it going? Are you a mathy person? Do you enjoy math? Have you done linear algebra before? Cool. Which other ones do we want to do? So we did that problem. Calculate this determinant. This one, I don't know. Was this interesting? I don't think it's particularly illuminating compared to the others that we've done. It's kind of just more calculation stuff. This one was cool though. Shilov 1.9 I liked a lot once I saw the solution on it. Calculate the nth order determinant. Love it. I'm in school right now for computer science. Heck yeah. And you're taking linear algebra now. Nice. What book are you using? Are you using Strang? We're doing Shilov right now. Shilov is tough as hell. Strang is pretty cool. A little bit easier, not gonna lie. In my college, we used first we used Frale for the first course, and then we used Friedberg, Insel, and Spence for the graduate course that I took. Yeah. What are you finding hard about linear algebra? Give me one of your problems. I'll help you with your homework. I'll help you cheat on your homework. Why not? All right, Shilov 1.9. Calculate the nth order determinant like this. This one is cool. I liked this problem a lot. So what I did was I calculated a couple, like a 2x2. So like, I called this delta 2 is the 2x2, xaax, and then I calculated delta 3, xaa, axa, aax. And I don't know if I calculated out the fourth determinant, but basically, yeah, if you pause the video and you try to do this yourself and you get a couple of examples, you'll start to see that, for example, this one is x minus a. Well, this one is easy. This one, a 2x2, you multiply across the diagonal, you get x squared minus a squared, and we know that that's x minus a times x plus a. When you do this one, you'll find that it turns out to be x minus a squared times x plus 2a. This is what I ended up finding. And then if you also do the fourth order one, you find that it's x minus a cubed times x plus 3a. I was really proud of finding this formula. Like, I found this one on my own, and I tried to prove it by induction. So you have those base cases, and then like what happens if you add an extra row and column. And it went okay. Like, I think I was getting an okay induction. It wasn't super clean. But Shilov has a really great hint that for the nth order determinant, again, this is xa dot 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 a ax dot 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 a you can add all of the columns to the first column. So if you add all of them together, then you get x plus n minus 1a, and you get that in every row. All of these are going to be x plus n minus 1a, dot, 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 x plus n minus 1a, a, dot, 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 then now we can factor out that common factor and say that this is x plus n minus 1a times the determinant with a bunch of 1s in the first column, and then a dot 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 a x dot 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 a now we can subtract a copies of the first column from every other column. 1, 1, dot, 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 1. And if we subtract a copies of the first column, let me rewrite this part. X plus n minus 1a. Yeah, if we subtract a copies of the first column from every other column, then the second one is 0. This one's going to be x minus a, and then zeros everywhere else. So all of these are going to be zeros everywhere except for the entry with an x, which is going to be x minus a. Then, now we can expand by the first row, and now this minor matrix, we're going to get x plus n minus 1a times the determinant with x minus a on the main diagonal and zeros everywhere else. So that one is going to be, remember that we expanded by this first row, so now this matrix is an n minus 1 by n minus 1 matrix. And the only entries are on that diagonal. So this is x minus a to the n minus 1. You multiply across that diagonal every entry times x plus n minus 1a. And that's your answer. That's it right there. And that I'm so proud that I did find that formula on my own, even if I didn't get a very clear proof of it. I had the beginnings of a proof. I had a proof by induction that was kind of working. But then when I looked at the back of the book and he suggested, like, add all of the columns to the first, then it just falls through. And, it works out really nicely. So, there's another one. Boom. Did another problem. That was Shilov 1.9. And now, I want to do one last one. This one was awful. But I think it's good for YouTube because I want to show... I did not do 110 on my own, but I did do 111. Like, this is so awful. I'm going to solve this one 2 different ways. And it will be a great illustration of how pointless determinants are. And maybe why Adler hates determinants. I don't know. Maybe that's why. But in this section, in Shilov, the only theory that he has in this chapter for how to solve a system of equations is... Oops. Alright, I think that we're still... Okay, yeah, we should still be live. Okay, the only theory that he has is Cramer's rule. I did not learn Cramer's rule when I took linear algebra. So Nate Programming, if you are taking linear algebra right now, let me know. Did you learn? Are they teaching you Cramer's rule in your course? It's theoretically interesting, but computationally it is not very efficient. It is like super inefficient compared to Gaussian elimination to solve a system of equations. But theoretically, it's really interesting. By Cramer's rule, a solution is going to be xi. You can calculate it by determinants. So we are going to replace the ith row in the determinant with the solution vector. I'm going to call the solution vector y. So if we calculate a couple of determinants, then we can get the value of x1 or any of them. So then again, I'm just going to write d. So we're going to replace the first column of coefficients with the solution vector, and then divide by the determinant d, where d1y is... again, we replace the first column of coefficients with the solution vector, 13, 10, 11, 6, 3, and then we write out the other coefficients, 2, 3, 4, 5, 1, 2, 3, 4, 1, 2, 3, 4, 2, 1, 2, 3, 2, 2, 1, 2, 2, 2, 2, 1. And 1. Okay, let's copy this whole thing. Erase that first column and write it with the original coefficients, 1, 2, 2, 2, 2. Okay, so getting some really good determinant practice. Practice, y'all. Let's get these. Let's do this. Let's start out with determinant D. Okay. Some patterns. Yeah, I see a bunch of 1, 2, 3, 4, 5s, 1, 2, 3, 4, 1, 2, 3, 1, 2, 1. And 2s along the bottom triangle. What's the best way to do this? I feel like there might be like a more clever theoretical way, because I just did it by hand and it took forever. Is there something smarter? I'm going to take the last column and subtract the fourth column. So 5 minus 4, 4 minus 3, 3 minus 2, 2 minus 1, and 1 minus 2. Subtract the third column from the fourth column. Again, we're going to get 1, 1, 1, and then 1 minus 2 is negative 1, and then 2 minus 2 is 0. Subtract the second column from the third. 1, 1, negative 1, 0, 0. Subtract the first column from the second. Then we get 1, negative 1, 0, 0, 0. And then leave the first column alone. Now, if we add 2 copies of the second column to the first, we get 3, 0, 2, 2, 2. One, negative 1, 0, 0, 0. Oh, wait. Wait. Is there something better we can do? Yeah. Let's add the fourth column to the fifth. 2, 2, 2, 0, negative 1. Okay, and then add the third column to the fourth. 2, 2, 0, negative 1, 0. Add the second column to the third. 2, 0, negative 1, 2, 0, negative 1, 0, 0. And maybe we leave the second column alone. 1, negative 1, 0, 0, 0. So we've gotten a bunch of zeros everywhere, and that's great. Now, if we add the last row, copies of the last row to other rows, then we can clear out the elements in the last column. So add 2 copies of the last row. 2 copies of the last row to the third row. So 2 copies of the last plus the third. So we've got 2 plus 4 is 6. 0, negative 1, 0. And then 2 plus 2 copies of negative 1 is 0. 0 plus 4, negative 1, 0, 2, 0. 2 copies of the last row to the first row. 4 plus 3 is 7. 0 plus 1, 0 plus 2, 0 plus 2, and then negative 2 plus 2. Now we're getting somewhere. We're getting somewhere. We could just keep doing the same kind of process. But here we can now do a cofactor expansion by the last column, which has a bunch of zeros and a -1. These are scary, right? Do you know determinants? Do you follow what I'm doing? Because, yeah, these determinants are gnarly. Like, this dude actually wants you to calculate these 5x5 determinants by hand. Shilov's just like, don't care, just do it, just get it done. Super gnarly. So, cofactor expansion by the last column. Positive, negative, positive, negative, positive. This is going to be -1 times the determinant of the minor. -1 times the 4x4 determinant. 7, 1, 2, 2. 4, -1, 0, 2. 6, 0, -1, 0. 2, 0, 0, -1. And now we're just going to do basically exactly what I was about to do anyways. So I don't know if it really is worth writing out the... I think it's easier to just keep doing row reductions on the full thing as opposed to rewriting it another time. I don't know, whatever. Doesn't matter. Keep the last row the same. 2, 2, 0, 2, 0, 0, -1. Add 2 copies of it to the second row to clear out that last column. So 4 plus 4 is 8. And then 2 minus 2 is 0. 4 plus 7 is 11. And now we're going to do the same thing with clearing out with the third. I'm just going to keep that last row. No, whatever. Let's get the example of how a cofactor works. Expanding by the fourth row, or fourth column. Signs are plus, minus, plus, minus. Plus, minus, plus, minus. So, negative, negative, and negative. This is going to be -1 times -1. So this is 11, 1, 2, 8, -1, 0, 6, 0, -1. And now add 2 copies of the third row to the first. So 12 plus 11 is 33. 1, 0. See, this is just so ugly, so gnarly to do these problems. 8, -1, 0, 6, 0, -1. Now, this is the negative determinant, 33, 1, 8, -1, which is -33 minus 8, which is -41. So this is D. Whew. All right, so we got D. We've done one of these so far, and we just have to do it again and again until our fingers fall off. And just keep calculating more stupid determinants all day long. This is how I spent my vacation in Cancun, everybody. Because I am an absolute nerd. Okay? I did it for you all, so that you all could learn linear algebra with me. Let's do the whole same freaking thing all over again. 6, 3. And now, subtracting columns from the fourth column from the last column. 1, 1, 1, 1, negative 1. 1, 1, 1, negative 1, 0. 1, 1, negative 1, 0, 0. And then, did I just leave the second column? I guess. 2, 1, 2, 2, 2. Okay. Add the third. Well, just add the last row to every other row. 3, 2, 0, 0, minus 1. Add the last row to every other one to clear out the last column. 6, oh wait, no. 6 plus 3 is 9. 2 plus 2 is 4. 0, minus 1. 1 minus 1 is 0. 11 plus 3 is 14. 2 plus 2 is 4. Negative 1. 1 plus 0 is 1. 1 plus minus 1 is 0. 10 plus 3 is 13. 1 plus 2 is 3. 1 plus 0. 1 plus 0. 1 minus 1. 13 plus 3. 2 plus 2. 1 plus 0. 1 plus 0. 1 minus 1. Great. Now add the fourth row to every other row. You know what? Instead of doing rows, I think it's way cleaner to add columns. Which we can add multiples of the last column to the first ones. Yeah, I think that this is way cleaner. Okay, so we can zero out the first, or the last column. We can zero out the other entries in the last row, is what I was trying to say. Now, add the fourth column to the second and first column. So basically we're going to add 4, or subtract 4 from the second column. So subtract 4, oh wait. Nope. Let's be careful. Add 4 copies of the fourth column to the second column. So 4 plus 4 is 8. 3 plus 4 is 7. 4 plus 4 is 8. And then add 9 copies of the fourth column to the first column. Then we have 0. So 14 plus 9 is 23. 13 plus 9 is 22. 16 plus 9 is 25. Okay, I feel like this is turning out a little bit nicer than what I did before. Okay, now I can add that fourth row to everything above. Well, let's copy in as much as we can. Let's copy in that little submatrix. Let's add in those zeros. And now I'm going to add the fourth copies of the fourth row to the other rows, which zeroes out the rest of that fourth column. And maybe this is a way that we can see how cofactor expansion kind of works out without actually, doing it. Positive. Yeah, I don't want to think about the cofactor stuff. So let's add copies of the third row to the first and second rows. So add the third row to the second row. We get 55, 15, 0. Third row to the first row, and we get 48. Oh, wait. Oh, shoot. I almost messed up. Oh, my gosh. Yeah, it's so easy to make mistakes in these determinant problems. This is 45. 22 plus 23 is 45. 25 plus 23 is 48. Whew. All right. 8 plus 8 is 16. 1 plus minus 1 is 0. We can factor out both of those minus ones, and then we have ones in that diagonal. Pretty confident that this is the same as this 3 by 3 matrix, but positive. Yeah, it is. 48, 16, 0, 45, 15, 0, 23, 8, minus 1. We can take out a factor of 4 from the first row and a factor of 5 from the second row. So this is going to be 20 times 12, 4, 0. We took out a factor of 5 from the second row, so this is 9, 3, 0. And then we still have 23, 8, minus 1. And now, well, we can expand by the third column. We can do cofactors across the third column, or we could just zero out this third row. We can take out a factor of 4 from the first row, a factor of 3 from the second row. 12 times 20 is 240. I'm going to minus 240 times the determinant. 3, 1, 3, 1. Is that really? Oh my god. Wait a minute. Is that right? Yep. Yeah, I'm actually, I remember this now. Yeah, so this is 0. Because anytime that you have a identical columns, or identical rows, then the determinant is 0. So, therefore, D1 substituting y equals 0. And then x1 is d1y divided by d, which we find is 0 divided by this other large determinant, which was completely pointless to figure out. D is negative 41. Complete, just giant waste of time. We just wasted a lot of time. That's how these determinant problems happen. All right, so we found that x1 is 0. Then I'm going to go back, and here was a realization I had, because I don't want to keep calculating 5 by 5 determinants all the time to calculate x2, x3, x4, x5. If we've solved for x1, then we can rewrite that system of equations. And now I can copy this I can duplicate this system of equations. And we solved that. We solved x1 is 0, so let's get rid of all the x1s. And now we have this new system of equations in 4 unknowns and 5 equations. So we only need 4 equations and 4 unknowns. We only need 4 equations for 4 unknowns. So that one, to me, looks the most complicated. 2, 3, 4, 5, and 13. We can just focus on this 4 by 4. And then we can solve for D2. We can solve for x2, and I'll call this D prime, replacing, technically it should be replacing the first column, I suppose, with y. The subscripts get confusing this way, but makes sense. Oh, y'all. These determinant problems are freaking gnarly. All right, and let's learn our lesson, because it's possible x2 is 0 as well, in which case we don't even need to solve for d prime. So let's solve for, and I'm just, by abuse of notation, going to call this d prime, d2 prime. Now these are 4 by 4 determinants. Again, we substitute the solution vector 10, 11, 6, 3 for the column that we're solving for. We're solving for x2. And then we write the other coefficients. 2, 1, 2, 2, 3, 2, 1, 2, 4, 3, 2, 1. Okay? And we just do this until our fingers fall off. Again, last column minus third column is going to be 1, 1, negative 1. Oh, wait, no. 1, 1, 1, negative 1. Third column minus second column is 1, 1, negative 1, 0. Maybe we keep the second column the same. 2, 1, 2, 2. And while we're at it, let's simplify and make our lives easier by subtracting. Let's subtract 3 copies of the second column from the first. So 10 minus 6 is 4. 11 minus 3 is 8. 6 minus 6 is 0. And then 3 minus 6 is negative 3. Hopefully that'll make our lives just a little bit easier. Now, hopefully, we'll see. I'm going to add copies of this last row to the other rows. So, 2 plus 2 is 4, minus 1 plus 0 is minus 1, 1 plus minus 1 is 0. 8 minus 3, 1 plus 2, 1 and 0. 4 minus 3, 2 plus 2, 1 plus 0, and 1 minus 1. Okay. Now, adding or subtracting copies of the last column from the other columns, the last row becomes this. And now I'm going to add copies of the third row from the second to the second and first rows. So 5 minus 3 is 2, 3 plus 4 is 7, 1 minus 1 is 0. And then 1 minus 3 is negative 2, 4 plus 4 is 8, 1 minus 1 is 0. Right? I know I could simplify this, but I just want to keep it as it is for right now. 0, 0 minus 1. So I'm subtracting and adding copies of the third column to the first and second. And now we have 2, 7, negative 2, 8. This is going to simplify to that 3 by 3 matrix. Negative 2, 8, 2, 7. So if I add the first row to the second row, then we get 0, 8 plus 7. 8 plus 7 is 15. And then this is going to be, I'm going to take out a factor of 2. I'm going to take out a factor of 2 from the first row and a factor of 15 from the second row. And we're going to get 1, negative 4, 0, 1. Right? So this is negative 30. And that was the numerator of x2. All of these are going to get easier and easier, but still they're a huge pain in the ass. They're like an enormous pain in the butt. More determinant problems all day long. This is how I spent my vacation because I'm a nerd. But I find it fun. I find it like quite meditative and fun, honestly. So I hope you do too. I hope you're pausing and trying these on your own as well. Kramer's rule is just so pointless. I'll show you all why. 1, 2, 2, 2, 2. After we're done with these. 1, 2, 2, 2. I should have just said, like, continue and you'll find the solution is blah, 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 but we're just going to do it all, apparently. 1, 2... Subtract third column from the fourth. 1, 1, negative 1. Oh, wait, no. 1, 1, 1, negative 1. Second column from the third. 1, 1, negative 1, 0. First from the second. 1, negative 1, 0, 0. Okay. All right, and now we're going to add copies of the last column to the others, or just think of it as a cofactor expansion, plus, minus, plus, minus. This is going to be the negative times negative 1 times this determinant of this minor 4 minus 1 1 4 0 minus 1. Adding the last row to the other rows, we have 4 0 minus 1. Is it easier to add by rows or add by columns? I don't know. I find it easier to add by rows. But 4 0 minus 1. 4 plus 4 is 8. 4 plus 3 is 7. 7, 1, 0. Okay, so now negative 7 minus 8 is negative 15, so this is positive 15. Therefore, x2 is negative 30 over 15. And again, that was the determinant substituting in the solution vector for that coefficient vector divided by the coefficient determinant, which is negative 30 over 15, and then x2 is negative 2. I'm going to double check myself. Hey, Mincheck, nice stream. Thank you. Thanks, man. I hope you're enjoying these determinants. How's it going? What kind of math are you studying? Have you studied linear algebra before? Mother effer. Okay, so we got negative 2, but the actual answer is positive 2. Where's the mistake? Negative 7. Oh, wait. Oh, here. That negative and that negative should have canceled out. And I think I had that at one point, and I corrected myself. Yeah, expanding by that third column, the cofactor -1, yeah, this should have been a -15 here. Which means that this would have been -30 over -15, which is +2. Jacob, hey man, how's it going, dude? I was just about to text you. I was just thinking about it. How are you feeling, man? How's it going? We are doing a bunch of determinant problems. I'm working Kramer's rule. I've got a nerd tan over here. I've got my V-neck nerd tan. I did a whole lot of linear algebra while I was in Cancun because I'm a nerd. I'm such a nerd, dude. Kramer's rule is so pointless. Like, I don't think my linear algebra class actually did Kramer's rule. Like, way back. I don't think I ever learned Kramer's rule back in the day. Because Gaussian elimination is just so much easier and faster. Like, more computationally efficient. So, this is a cool thing to learn. Alright, so we just solved for x2, which is +2. And so far, our solution, x, is 0, 2, something, something, something. This is a 5x5 determinant problem because Shilov is an asshole. And our system of equations now, we're going to solve for x3 to be, I'm going to simplify this matrix again even further, substitute the solution vector, and then divide by this other matrix. So this system of equations is now going to become, we're going to replace x2 with 2 everywhere. Then d double prime y. So this, subtracting 2 from both sides, this is now an 8. Subtract 4 from both sides, this is a 7. 4 from both sides, and this is a 2. 4 from both sides, and this is a -1. Now we're getting into easier territory. This first equation seems more complicated than the others. Let's focus on these last 3 equations and 3 unknowns. Substitute the solution vector for the column that we're interested in for Kramer's rule. 2, 1, 2, 3, 2, 1. This is a 3x3. We could just calculate it using the formula, copying the first 2 columns, and then doing the diagonal Sarus's rule. But now we've gotten so good, and we just love doing these determinant problems so much that we're going to just do it the other way by reductions. So subtract 2 copies of the third. Oh, wait, no. Again, we're going to subtract the second column from the third, and we get 1, 1, -1. And then 2, 1, 2. Maybe we'll subtract the second column from the first. 5, 1, -3. Now add the third row to the other rows. Then, yeah. Okay, so we got the numerator is negative 14 over d double prime. D double prime is 1, 2, 3, 2, 1, 2. 1, 2, 3, 2, 1, 2. 2, 1, 2, 2, 2, 1. 2, 2, 1. Doing the same sort of tricks that we've been doing the whole time through. Subtract the second column from the first. 1, 1, negative 1. Then the first column from the second, 1, negative 1, 0, and then keep the first column. Now, add the third row to the second and first row. So 3, 1, 0. 2 plus 2 is 4. And now we get negative 1 times the 2 by 2 determinant. 3, 1, 4, minus 1, which is negative 3 minus 4. So this is 7. All right, and these are looking good. Things are looking good. X3 is then negative 14. Again, this is d double prime. Substituting the column vector for the solution vector, and we found negative 14 for the numerator, and then 7 for the denominator. That sounds like a nice number, negative 2. Hey, L.S. Dominguez, how are you? First time in the channel. How are you, man? Thanks for stopping by. And yes, that's the answer in the back of the book for x3. So far, x is 0 to negative 2, something, something. And we're getting so close. We can just taste it. We're getting so close here. Let's copy all this again. And then we've got a lot to erase and whatnot. How's it going? I hope you all are enjoying this. Math stream. Okay, and we get rid of all this stuff. All right, so we were focused on this 3 by 3 system of equations, and now we just solved for x3. x3 is negative 2, so maybe in red, this is a negative 2, this is a negative 4, then 7 plus 2 is 9, 2 plus 4 is 6, negative 1 plus 4 is 3. So now here is our new equation. 3 equations, 2 unknowns. We only need to focus on 2 of them. Let's solve for x4 is d triple prime 4 over d triple prime. And now these are getting easier and easier. I'm actually going to write it all in line this time for the first time. So again, we substitute the solution vector into the first column, into the column that we're solving for that unknown. So this is 6, 3, and then the others are 2, 1. What? All right. Well, that looks like 0 because the first row is 2 copies of the second. So because of the linear dependence of rows or columns, then... Hey, thanks, Jacob. Let's talk soon. Let me text you. Let's find a time to chat. Would love to catch up. And thank you. Thanks for the handwriting compliment. I appreciate that very much. Yeah. So good to see you, man. Thanks. Thanks so much. Talk soon, dude. Yeah. And thanks, LSD Alminguez. Thank you. Thanks. I'm glad that you enjoy this. It's really fun for me to be brushing off all of this material because I have not been really doing math in a long time. So this is 0 over something. We should whatever. Let's actually calculate this. This bottom determinant would be 1, 2, 2, 1. Which is going to be 1 minus 4, which is negative 3. So x4 is 0. Again, we've got 0 to negative 2, 0, and then something, x5. And we can substitute in 0 for one of those x4s. If we just look at this one, then 2x5 equals 6. So then therefore x5, 2x5 equals 6. Therefore x5 equals 3. And then 0 to negative 2, 3. Oh, wait, no. 0 to negative 2, 0, 3. Is this the final answer? Is this what the back of the book has? I'm going to be so happy if I didn't make any major mistakes. Yep, that's it. Yeah, we did it. We did it. We solved this stupid freaking problem. It's like pages and pages of determinants to solve. Like, was this really necessary, Shilov? Like, did you really need to do a 5x5 system of equations for Cramer's rule? Like, was that the best use of all of our time? I don't think so. Why am I complaining so much? Well, here's why. Let's get that original system of equations. Again, I mentioned this earlier. I did not learn how to solve a system of equations this way. When I was in linear algebra, my teacher didn't teach Cramer's rule. Or maybe it was mentioned and we promptly forgot it because this way is just way better. And I don't know where Shilov teaches this. I'm going to say solution 2 by Gaussian elimination. This way you don't calculate determinants. Instead, you do row reductions on an augmented matrix. So I'm writing out the coefficients of these equations, and then we're augmenting this matrix with an extra column, which we denote with this. We just remind ourselves that it's augmented by drawing a line there. 13, 0, 11, 6, 3. 2, 1, 2, 3, 4. 2, 2, 1, 2, 3. 2, 2, 2, 1, 2. 2, 2, 2, 2, 1. Okay, by Gaussian elimination, this is another approach to solve a system of equations. With this approach, you again do these row reductions of subtracting or adding copies of rows from one another. So with this, you don't add and subtract columns. I don't think that you can. you pretty much only focus on rows. So, let's take the first row and subtract, well, I don't know. 1, 2, 3, 4, 5. I don't know what the most clean way is. We want to get rid of all these 2's primarily. Like, there's all of these like common 2's. So let's subtract the 4th row from the 5th row. So row 5 minus row 4. 2 minus 1 is 1. 1 minus 2 is negative 1. 3 minus 6 is negative 3. So this was, again, row 5 minus row 4 here. And now here, I'm going to also do row 4 minus row 3 at the same time. Row 4 minus row 3 is 0, 0, 2 minus 1, 1 minus 2, 2 minus 3 is negative 1, and then 6 minus 11 is negative 5. Right? Third row minus the second row. Third row minus second row is going to be 0, 0, 0, 1, minus 1, 2 minus 3 is minus 1, 3 minus 4 is minus 1, and then 11 minus 10 is minus 1. Oh, wait, no, is positive 1. And then second row minus first row, I guess. 1, minus 1, minus 1. 3 minus 4 is minus 1. 4 minus 5 is minus 1. 10 minus 13 is minus 13. And I kept the first row the same. Row 2 minus row 1. So there I wrote all my substitutions that I did in this one step. Now, the goal is to get the identity matrix on the left. If we can get the identity matrix on the left part of the matrix, then the right-hand side, like after the augmented bar, that is going to be our solution vector. So we don't say that they're equal, but we've got this like similarity, like augmented symbol thing instead. So I'm going to keep this last row the same, but I'm going to add the last row to the others. 0, 0, 1, 0, minus 2, and then negative 5 minus 3. We added those to negative 8. 0, 1, negative 1, negative 1 plus 1 is 0, negative 1 plus 1 is negative 2, 1 plus negative 3 is minus 2. Second row plus fifth row is 1, negative 1, negative 1, 0, negative 1, minus 2, negative 3 plus negative 3 is negative 6. And then we could add 4 copies of the last row, or subtract 4 copies of the last row to the first one. Yeah, let's just, I guess, clear out that column of zeros. So here we've got row 1 minus 4 times row 5. Let's use some subscripts so this looks a little nicer to me. Row 1 minus 4 times row 5. So I'm really like focusing on where we have a bunch of zeros so that like adding and subtracting multiples of 0 is easy. So these first numbers are the same. 1, 2, 3, and then 4 minus 4. 5 minus negative 4 is the same as 5 plus 4. And then 13 plus 12. 13, yeah, plus 12 is 25. Okay. I'm not going to write all the row reduction steps. I said them out loud. In Gaussian elimination, you can swap rows, and you don't need to be concerned about changing the sign of the value of a determinant or anything. But actually, let's just keep it as it is for right now. I want to add this fourth row to the others. Or I can see that here we've got this nice leading diagonal of 1s. So I am going to go ahead and swap rows so that the last row I'm just going to rewrite here. 1, 2, 3, 0, 9, 25. And then rewrite everything else. 0, negative 2, negative 6. 0, 1, minus 1, 0. 1, 0, minus 1, 0, negative 2, negative 2. 0, 0, 1, 0, negative 2, negative 8. And then 0, 0, 0, 1, negative 1, negative 3. Okay. So my goal is to clear out all of these and make those zeros. So we'll need to subtract copies of the other rows to make that happen. So we've got row 5. We're going to subtract 1 copy of row 1. We're going to subtract 2 copies of row 2. We're going to add 3 copies of row 3. And then we'll pause there. Okay, so that's going to get us zeros here by construction. Row 5 minus row 1, 9 plus, so far we have 9 plus 2, minus 2, so plus 4, and then plus 3 times row 3, so minus 6. 11, 15, 9. Really? Yeah, okay. And then we've got 25 minus row 1. So I'm looking at the coefficients in the or in the solution vector thing. 25 plus 6 minus 2 times row 2, which is going to be a positive 4. 3 times row 3 is a negative 24. 25 and minus 24 is a 1, so 7, 11. We did not get the right answer. No! Oh well. Oh well. We're bound to make a mistake somewhere along the way. I was trying to show off how much nicer Gaussian elimination is compared to everything else, but we made a mistake somewhere. Because we should get something that gives us 3 as the last solution. But, so I made a mistake somewhere in one of these steps. I bet that I was doing fine before, and here I tried to get way too fancy. Okay, row 5 minus row 1. Oh, I know what's going on. Yeah, okay. Yeah, I tried to get way too fancy here. That doesn't work. Okay. Slow down, John. Slow down. Step by step. Row 5 minus row 1. That's going to give us a 0 here. 2 minus negative 1 is 3. 3 minus negative 1 is 4. 0. 9 plus 2 is 11. 25 plus 6 is 31. Okay. So maybe y'all can see what was going wrong. Everything else is the same in this matrix, so I'm just going to only be writing the last row to save some time. Row 5 minus 3 times row 2. Okay, so then row 5 minus 3 times row 2. 0, 0. 3 minus 3, 4 plus 3 is 7. 0 plus 0, 11 plus 6. 11 plus 6. Is that right? Okay. 31 plus 6. Yeah, 31 plus 6. This is confusing me to try to just reference old matrices, so I just want to write it. 0, 0, 1, 0, negative 2, negative 8. 0, 1, negative 1, 0, negative 2, negative 2. 1, negative 1, negative 1, 0, negative 2, negative 6. It would probably clean up some things if I just, yeah. I think it would clean up some things if I added other rows in between. So I'm doing row 1 plus row 2. And now I'm doing row 2 plus row 3. Next, I'm just keeping row 3 the same. keeping row 4 the same. And let's write this one. So now we need to subtract 7 copies of row 3 from row 4. 0, 0, 0, 0. So 7. So 14 plus 17. Whew. Negative 8 plus negative 8 times negative 7 is 56. 56 plus 37 is, wait. Okay, this didn't work out either. All right. Okay. Didn't work out. What went wrong this time? Wait. Oh, well. So, oh, well. So my point was I was trying to show off how much better Gaussian elimination is. And I made a mistake somewhere in one of these little, like, additions and subtractions. This is such a good way to just practice mental math again and just like a little puzzle. Just try to practice your mental math. I made a mistake somewhere because here we're not getting x5 equals 3 as we should have. But the point is, I think that you can see that we're getting pretty close and we're almost done to be able to solve for that right-hand side. And the basic operations that we're doing, adding and subtracting rows from each other, adding and subtracting copies of rows to get a bunch of zeros, like in a column or in a row, that is the same approach that we were doing to calculate determinants. And with Cramer's rule, you have to calculate all of these determinants again and again and again, like many times. So we had to calculate 2 5x5 determinants. And then I was at least clever enough to see that we can replace that first coefficient. And then we have to calculate 2 4x4 determinants, and then 2 3x3 determinants, and then 2 2x2. So, and calculating one of these determinants is pretty similar in the number of steps, the number of calculations that you need to do to calculate a Gaussian elimination one time. So Gaussian elimination is generally, I think, a lot faster than Cramer's rule. And if I went back, I'd probably find where we made a mistake. I could try again. But I'm getting kind of tired. I bet if we started over, let's keep all those mistakes. I bet if we started over from here, I think we definitely find it. I'm so determined, right? Yeah, dang, and I thought 3x3 was bad. No, 3x3 is not bad, dude. Good to see you, Math Spellbook, by the way. 3x3, you get to just do the nice, simple, I'm going to say 1, 2, 3, 4, 5, 6, 7, 8, 9, although I know that is 0. With 3x3, you get to copy the first column and the second column, and you get to do this lovely Sarus's rule. This is called Sarus's rule. and you add the yellow multiplications and then subtract the blue multiplications. Yeah, 3 by 3 is not so bad. 5 by 5, insane. Shilov is so horrible to us. Shilov has been very mean to us. But I'm so determined to get these. So I do want to. I want to get this. 1, -1, -3. I want to add that to the other rows. 0, 0, 1, 0, -2, -8. Add the last row to the third row. 0, 1, -1, 0, -2, -2. Second row plus the last row. 1, -1, -1, 0, -2, -6. And yeah, it's just so easy to like accidentally add instead of subtract and things like that. You have to be like really careful with these. 1, 2, 3, 4, 5, 13. I'm going to keep that one the same this time. And now I want to add the fourth row. 0, 0, 0, 1, -1, -3. I'm going to add the fourth row to the third row. 0, 0, 1, 0, -2, -8. 0, 1, 0, 0, -4, -10. And then add the fourth row to the second row. 1, -1, 0, 0, -4. -6 minus 8 is -14. And then let's keep this first one, which is trickier, and we'll have to be a little bit more careful not to make a mistake with. I want to 1, 2, 3, 4, 5, 13. Add the third row to the second. 1, 0, 0, 0, -8, -24. Zero, 0, 1, 0, -2, -8, and 0, 0, 0, 1, -1, -3. Okay, so we're getting somewhere. We're getting somewhere. I'm going to subtract. Oh, wait. Subtract the second row from the first. 3, 4. So 8 plus 5 is 13. Oh, wait. And then, sorry. First row minus second row. So 13 plus 24 is 37. Great. 1, 0, 0, 0, -8, -24, etc. Subtract 2 copies of the third row. Two copies of the third row from the first. 0, 0, 3, 4. So if we 8 plus 13 is 21. 20 plus 37 is 57. And then the next row is 0, 0, 1, 0, -2, -8. and then some other stuff. We are going to subtract 3 copies of the 4th row from the first. 0, 0, 0. 4 minus 0. So 6 plus 21 is 27. Oh, wait. Yeah, 3 copies of that row. I think of it as like negative 3 times... negative 3 times 2 is 6, plus 21 is 27. So negative 3 times negative 8 is 24. 24 plus 57 is 81. 24 plus... Yeah. And then we've got a bunch of stuff, and we have this row 0, 0, 0, 1, negative 1, negative 3. And we're going to use that. So I'm not touching any of the other rows. I'm only adding and subtracting to the first row. I'm always like copying, changing the first row. 0, 0, 0. Subtract 4 copies of the last one. That is, we are doing R1 prime is R1 minus 4 times R5. So 4 plus 27 is 31. 12 plus 81 is 93. And boom, we're getting somewhere. Because this one is the correct answer for that first row. 0, 0, 0, 0, 1. Divide that entire row by 3, and then the right-hand side is a 3. And then let's copy everything else. I'm going to try to copy all that here. And copy this here. Okay. Now, if we rearrange well, let's not rearrange things. Let's add 8 times the first row to the second. So 8 times 3 is 24. So we found that the first value is 0 as we wanted. 0, 1. Now we're going to add 4 copies of the first row to the third to clear out that coefficient. So 12 minus 10 is 2. We will, where are we? Add 2 row 1s, add 2 times row 1 to row 4. 0, 0, 1, 0, 0. So 2 times row 1 is 6. 6 minus 8 is negative 2. Hey, look at that. Those numbers are looking familiar as hell. And then we add the first row to the last row. 3 plus negative 3 is 0. and then the last row, 0, 0, 0, 0, 1, 3. And boom. Therefore, our solution vector is 0, 2, -2, 0, 3. Exact same answer as Shilov for this problem by Gaussian elimination. And I will claim that, yeah, I messed up. I had to restart. I had to do it again. But the math here and like the amount of care and being careful about adding versus subtracting and like the type of math that you're doing of like these row reductions, it's not any different than doing it for determinants. Like with Kramer's rule, you have to calculate these 5 by 5 determinants. And I don't know that it's any easier than doing it one time with Gaussian elimination. So that's just another approach, and it's the same. Yeah, you got to the same answer. Cool. I hope you all enjoyed. I remember I was doing a lot of cross-product problems, and I was totally worn out. Yeah, well, hey, if you're doing cross-products, you should absolutely know about Sarus's rule. Sorry I haven't been responding to chat. I've been so zoned in on this problem. Always scared of linear algebra. What would be the best approach to learning it? I don't know. Honestly, I don't know. I'm not a good teacher. I'm learning this all again on my own. I'd say tune in to the channel and ask questions. This book is probably the best one that you want. A lot of people recommend Strang, and his lectures are really great. And we will be working from Strang as well as Shilov as well. So, I don't know. Yeah, like, it's really great stuff. I think doing problems that are smaller in scale and working your way up. Yeah, absolutely. Start with vectors, matrices like 2 by 2, 3 by 3. Yes. Yeah, Shilov just jumps right into like super difficult, hella hard, n-dimensional determinant problems. Like just, he does everything from the definition of like, based on permutations, and it's pretty gnarly, like super gnarly. You learn about linearity, absolutely. Yeah. I would like to create a habit. Oh, yeah. Thanks for your advice. I have books, but I get lost on the problem at specific points, and then I give up. Yeah, just let us know. Bring a problem that you're stuck with. Bring a problem that you're working on, and we could all solve it together if you want. I think that'd be really cool. And yeah. Strang is a great book to use for your first experience with linear algebra. Great idea. Okay, everybody, I am super tired at this point. Quite literally, I was doing all these determinant problems on the beach while I was in Cancun last week, so I'm happy to share a few of them with you all. This last one was a pain in the ass. I was like, I'm done at this point. So yeah, I hope you enjoyed. Go back, check out the rest of this video if you want to see some other cool problems. And yeah, like and subscribe, everybody. I hope you enjoyed this. This was fun. Thank you for tuning in. Hopefully, for the rest of the week, I want to move on from just doing determinants left and right. I want to get into some cool applications of linear algebra. This week, my goal is to start really learning about Markov chains in detail. So I think tomorrow I'll be introducing the characteristic polynomial and briefly talking about eigenvalues and eigenvectors. Spoiler is that the characteristic equation, you can think of it as the determinant of your matrix minus lambda I. When the determinant of this matrix equals 0, that's how you get the characteristic equation. And you can find eigenvectors, eigenvalues, lambda, and eigenvectors. These are vectors such that your matrix times that vector equals a scalar factor of that vector. Like if you subtract lambda v from both sides, av minus lambda v equals 0, then a minus lambda I times v equals 0. So we want to find, if you want to solve this equation, it's equivalent to that matrix equaling 0. And if the matrix equals, well, I don't know. Yeah. If this equation equals 0, then we know that the determinant of that matrix, A minus lambda I, has to equal 0. So, yeah. Soon we're going to be learning about eigenvalues and eigenvectors and applications to Markov chains. Thanks everybody so much for watching and for hanging out. My name is The Math Hobbyist, or John, whatever you prefer. Like and subscribe and share. If there's anybody else that you know who you think would enjoy this, who would enjoy like studying together and doing math together and bringing cool problems to work on together, share this stream with them. I'm on almost every day, if not every day, and this was super fun. Yeah. All right. Thanks everybody for watching. Bye. Hope to see you again. Hope to see you again soon. All right. Bye everyone. Thanks for watching. Hit the like and subscribe. Later, y'all.